What's up? This is Matt Brown with another IoT hacking video. Today we're going to take another look at the Smart Scale device from the previous video. We are going to talk about some of the setbacks I had in the analysis of that device and the steps forward that I've taken with some of the hardware reverse engineering work. I'd like to thank everyone for continuing to watch my videos and commenting and subscribing. Please tell me in the comments how I can continue to make videos that appeal to you. So without further ado, I'm going to share my screen quickly and talk about that setback that I mentioned very briefly. So over here on my screen, I have the FCC site. This was discussed in part 1 of Hacking the Smart Scale. And I said that this was a wealth of information, that we can learn a lot from these documents on the FCC's website. This isn't the FCC's website, this is just a mirror of the content that is on the FCC's website, but that we could get a bunch of data from this about our device. It turns out that this device here, you can see it's called DARA2. That's the name, the model number, the model name and number of this scale device, and I have the DARA1 scale, which, as it turns out, there doesn't seem to be a listing in the FCC database for the DARA1 scale, which raises a whole set of questions that I do not have answers for. But as it turns out, some of the internal photos that I was using to understand parts of the system, turns out they don't really apply. And I mentioned that in the video that my device looked different. The circuit board, the main circuit board, looks different. And so this kind of set me back because I wasn't able to use any of that information from the FCC website for this project. So with that, I'm going to head back to the desk and kind of take another look, another stab at trying to figure out what's going on this board. So I'm going to flip over to the desk. Obviously, we've got the scale here, and so we've got the main circuit board here, and on the flip side of this is actually the LED display as well. So all of those components are here, and then just as a refresher, so these right here, these components on the scale are both the weight sensors. So when this is pushed up on from the other perspective, but pushed down on, when you stand on the scale, it registers the person's weight, and then it also sends an electrical signal through the person to do the body fat, the BMI calculation. So those are the two primary data points that you get out of this smart device. So I needed to go back to the drawing board, go back to the PCB, and we're going to try to see what else we can figure out on this device. So we're gonna pull up the microscope, get all the way zoomed out as far as we can go, and we're just gonna review what we saw before. So before we identified, I'll grab some tweezers here to point with, this main board here, and we identified this SoC, and all of the data sheet information about this chip right here that we talked about in the last video, all of that still stands. That chip is capable of transmitting Bluetooth. It's a full implementation of the Bluetooth stack in this SoC, and then it also houses an ARM microcontroller. Now, my hypothesis is that this microcontroller, it can be a full-fledged, it can act as the main application microcontroller for this entire device, and that was my hypothesis. And then I just kind of ignored what was underneath this blob of chip top, chip off. There's a bunch of different names for this, some sort of epoxy. I definitely want to investigate in the future what type of heat or chemicals that I need to remove something like this without damaging the components underneath. That's a key part of that. If anyone wants to give me suggestions in the comments, I would appreciate that, because I think that might be a good future video of demonstrating how to remove this, and so I can learn as well. But let's just assume that I'm not going to remove that. There's some interesting traces that I noticed on the board that made me think that the brains of this whole smart scale operation are not really up here. So the second hypothesis would be is that this is merely being used for the Bluetooth transmitting, and that the main microcontroller application is being housed underneath this black blob here. So obviously, like I mentioned, I want to someday try to take this stuff off and see what's going on under the hood, under the blob there. But what I can do in the meantime is look at any communication paths between whatever is under this blob and our Bluetooth module up here. And so that is what I have done. So I'm going to get my microscope all the way zoomed in here. And I already have one wire that's popped off. So that's good, because I wanted to give an example of how I solder onto these small traces here. So you'll see, I'm just gonna zoom in all the way there. You'll see here on the circuit board, so obviously the white layer on this circuit board is a solder mask, right? It is non-conductive and it protects all of the copper traces here. And you can see here I have one that I've scraped off. I've scraped away at the coating that's sitting over top of a trace. And you can see that this trace is running from this circuit board up here all the way down into our blob. So my assumption is that some of these traces that I see going between the SoC that's exposed and the blob, that there's some sort of communication channel between these two components. And spoiler alert, there is. So right now, I'm going to pull out my soldering iron. By the way, you can see the ones that I haven't tinned with solder. Those I discovered were connected to ground, and therefore it would not be that interesting for me to spend the time to solder up these very delicate jumper wires too. So I am going to, though, take this one. We're going to get underneath the microscope here. So obviously beforehand, I did not know that there was anything valuable being transmitted on these signals. So this was just a hypothesis that I tested. Okay, so there, I still have some flux down on the board, so that's going to hopefully help me make this connection. Ooh, that doesn't seem like a great connection, but we will find out. We will find out if that succeeded. But while we're down here on the board, I am going to give an example of how I scrape away at these traces. And so I'm going to do that by just going over here and scraping at this trace that I know is connected to ground because it's connected to another component down here that I was able to verify that's not underneath the blob. But see, you just kind of, I'm just using a tweezer and I'm just scraping back and forth and getting enough so that I expose enough copper there. And obviously you can like use some alcohol or something and clean off all this residue. I have not done that yet, but that's how we scrape away at something and expose copper so that we can solder onto it. And then this other trace there that has solder on it, there is a signal on there. It's not the most important signal, but just to demonstrate again. And I am going to throw down a little bit more flux. And this is so tiny that this would be almost impossible for me to do this type of thing without a microscope. Not saying it's not possible. I did a lot of stuff before I had the microscope, but it just helps a lot when you're doing stuff like this. So I'm gonna get the solder hot. And now we're connected. Okay, so we've got our 3 wires connected to our 3 traces. And now we're gonna go see on the logic analyzer if that middle trace is actually connected. I am not highly confident in that solder job there. And like I said in past videos with this magnet wire, if you bump it the wrong way, these are going to come loose, but this is just for analysis. This is just for a quick analysis. I am not going to attempt in any way to be putting the scale back together with these wires on those traces. So, and with that, let's shoot over to here. So in one of my last videos, I had a lot of really good feedback about how to use my logic analyzer better. So one of the pieces of feedback I was given was to up this sample rate, which I have. So I've definitely upped the sample rate. I think I was like at like around here, bare minimum. So I've upped that. I think that helps. I'm still guessing baud rates, so that's just how I do it. So now we're gonna go back, and so I cleared out all our analyzers. And I have this scale. Another kind of thing I might try to show on my desk sometime. It's kind of hard to show, but back here I do have a power supply that instead of having the scale is typically battery powered, but right now I have it connected up to the power supply and the battery's removed so that I can just turn it on and off with my power supply. So that is pretty convenient. So right now it is off, which is great. So I'm gonna hit start on my logic analyzer, and then I'm gonna go over here on the desk and hit on. Yes. Okay. All 3 solder jobs look good. All right. And so you can see I'm getting something on all of them, but it's looking like channel 1 and channel 2 are where we're getting some interesting data. So I'm gonna go ahead and hit stop for now on that. And we can zoom in on these signals here. Okay. That solder, that was, I wanted to see that I was actually getting a signal there to see if that solder job was correct. So for hit here, we're going to put in a couple analyzers for these 2 channels. It's going to be asynchronous serial. So for the first one, yeah, it's going to be on, it's actually going to channel 0 and channel 1, excuse me. And then I, through guessing and checking, figured out that this was the right baud rate. Everything else is default. This is a standard UART connection with all of those defaults. Okay, so I set that analyzer on this, and so there I'm getting these nicely decoded bytes, and more on the content of these data bytes later. So now I have to add another analyzer for channel 2. So this other channel, all it does is it just really quickly goes up high briefly at certain points, and it seems to be correlated to, has something to do with these other 2 data transmissions, but the other ones are much more interesting. So I'm going to add another async serial. I'm going to go on channel 2, hit save, and now I'm getting similar, a number of bytes all being transmitted around the same time. And then the other cool thing is to notice how it seems like we can see here that it's clearly one channel is transmitting some piece of data, and then the other side responds back. So that's really cool here, and it seems that they share a protocol, a binary protocol, because you can see here the same start bytes here, the AC02, AC02. Those are, and some of these other bytes are the same as well. And then this end byte is the same. I wonder why that is. I might know. So this is a very interesting process, and especially on startup, there's a lot of activity from this one channel that occurs at device startup. But then something also very interesting happens when I take a scale reading. So I'm gonna wipe out that result, hit start, and then I'm gonna come over and I'm gonna push down on all 4 of the scale pads at one time to simulate someone standing on the scale. And then I'll let up, and it transmits for a little bit, and eventually it'll stop. At least it did last time. There we go. So that data transmission, that was not me turning the device on or off. It had been on for a long time, but this is directly in response. These signals going between those 2 chips on the board is directly as a result from me weighing in on the scale. So I'm going to hit stop, and then I'm going to zoom in on some of these packets again, because I just find this really fascinating. And in this case, it's all coming from this channel 2, channel 0, which before we kind of saw it was a request response type of an activity. This is all most of it. We do see some transmissions at the beginning and at the end of the weigh-in, which is again very telling that these 2 channels are probably a TX and an RX between these 2 components. But I want to go look at some of these values here. And right here, okay, so this message right here is really fascinating, because this one, this data here, and maybe I'll go to the end where it's going to give me a 0 there. Let me go to like the end. Aha! So here it's like all zeros in that packet. And I say packet because this reminds me of something that I've observed from another part of this system that I've been analyzing, and that is the Bluetooth traffic itself. So when I use the Android application on my phone and I weigh in on the device, I observed some pretty similar data. So here we can see AC 02 00 00 00 00, and then CE CE. So that exact piece of data corresponds to what I see in, here it is. So these Bluetooth packets that get sent over the air to the Android app, there is that same exact payload. So this is just part of the Bluetooth packet, right? So this is just the application data, the payload that this system is using Bluetooth Low Energy to communicate between the scale. It's from the scale sending to the Android or the iOS mobile application using Bluetooth Low Energy. And then you might ask, ooh, how did you get this Bluetooth Low Energy data? Well, I would love to do a video on that. I might in the future, but that is also something that if you're in Wisconsin and you you want to come to a security conference later this year on March 30th, I'm actually giving a talk on this device. So in this talk, I will be detailing some of this hardware reverse engineering that we talked about in this video, and more hardware reverse engineering that I've done. And I'm also going to discuss the vulnerabilities that we have discovered in the Bluetooth Low Energy communications between this device and the mobile app that does put the user's data at risk. So more on that to come. Looking forward to sharing the results of our CVE findings and everything that comes with that, blog posts. But that's something that I'm looking forward to, and this has been a fun adventure. I had no idea when I started out looking into this scale that it was going to turn into something like this, but it did. So I'd like to thank everybody for watching this video, and everyone have a good day.